welcome to my channel again. So we'll continue with Gauss Markov theorem. So today we'll discuss the variance. So according to our assumptions, in blue, that means best linear unbiased estimators, according to our assumptions that the estimate should be unbiased, that we have already proved in earlier lecture, and the variance should be minimum. So today we'll discuss number 3 is that the variance is minimum. Now estimated variance of an arbitrary beta taken from samples is equal to variance beta 1. That means that beta 1 is the true beta of estimate from population plus sigma u square into some di square. Okay. So beta 1 estimated is equal to some ki yi, and ki nothing but xi divided by summation xi square. So we have already got it. And variance beta estimated beta is equal to variance ki some ki yi. So for beta 1 we can substitute this, and some variance, if we take the summation sign outside, variance ki yi. So this can be written as some ki square into variance y. So this is equal to k square sigma u square is equal to sigma u square sum ki square. If we take the sum ki towards the end. Okay, now we'll see that. So by similar analogy, the estimated, that means the arbitrary beta is equal to ci yi, and variance of arbitrary beta estimate is equal to variance some ci yi is equal to ci square variance yi. Okay. Ci's are given constant weights. What we assumed in earlier lectures, what is ci is nothing but constant weights independent of yi's. But variance of yi is equal to sigma u square. So I have shown here now variance of yi is equal to expected yi minus expected yi square is equal to sigma u square. Now if we substitute the value of yi, what is yi? Yi is nothing but beta naught plus beta 1 xi is a straight line. So our assumption was that the linearity in Gauss-Markov theorem, linearity is the first assumption. So it is linear, that beta naught intercept plus beta 1 xi. Now expected yi is equal to beta naught plus beta 1 xi. Okay. So variance beta 1 or arbitrary beta is equal to sigma u square into some ci square. Now what is ci square? Ki plus di square is equal to, that means a plus b whole square is equal to a square plus b square plus 2ab is equal to some ki plus some di square. Now ki di, okay, ki di, this term, ki di is 0, as we'll show that ki di is nothing but some xi divided by some xi square. Okay, that means some ki di means some xi divided by some xi square into di. Now what is this? Is small x. What is small x? xi minus x bar, that is mean deviated x, into di by xi square. So this is equal to summation dixi minus x bar sum di divided by summation xi square. So since di is 0, that is both the terms are zeros. Okay, both the terms are 0. So this term, that means summation ki di, this term becomes 0. Okay, this term. So this term is 0. So remainder is summation ki square plus summation di square. So how this term is 0, I have shown here. So sum di is equal to 0. Now variance of beta 1, arbitrary beta 1, is equal to sigma u square into sum ki square plus sum di square is equal to sigma u square into sum ki plus sigma u square sum di. Okay, if we remove the bracket, but sigma u square by sum ki square is equal to variance beta 1. So variance of beta 1, arbitrary beta 1, is equal to variance beta 1 estimated plus sigma u square sum di square. As di's are arbitrary constant weights, the second term, sigma u square plus summation di, is positive. So this term is positive, and variance beta 1, arbitrary beta 1, is greater than variance beta 1. So that means beta 1 is smaller. Beta 1 has minimum variance. So this is another theorem of Gauss Markov theorem are examining that the variance of the regression coefficient of a linear model is the minimum or least. So with this we have concluded the unbiasedness and variance of estimates proved by Gauss-Markov theorem. So in the next discussion, we'll go for intersect. So far we have discussed the estimate. That means where is that? We have discussed about the unbiasedness and variance of beta 1, but we have not discussed about beta naught. So in the next discussion, we'll discuss the unbiasedness and variance of beta naught through Gauss-Markov theorem. So thank you very much for watching, and go on watching. We'll meet again. Thanks.